Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be relating the electric potential to the electric field. So this is a continuation of our calculus-based introductory physics series on the electric potential. This one is probably a bit more of a stretch for a Physics 2 video. Simply because many of you who are taking Physics 2 are only just now taking Calculus 2, integral calculus. Maybe you've made it into Cal 3 at this point, maybe you haven't. I by and large expect that most of you probably haven't actually seen stuff like electric potential at this, excuse me, I largely expect that most of you taking this course, we've been doing some line integrals and surface integrals and that kind of thing. And many of you probably haven't seen those things before outside of physics. And you've also not seen before the sort of inverse function of a line integral, which is the gradient function. And so we're going to be digging into all that today. To get into where this video's motivation is, partially, let's recall where we've kind of been so far and what we've seen. We've seen electric fields and we've seen electric potentials. So what does each one of those do? Well, electric field, often represented by a vector E, relates force per unit charge due to the presence of other charges everywhere in space. So in some sense we might write something like that the force acting on little q charge is Q times E. And then electric potential, which is voltage, V, what that one does is it relates energy, specifically potential energy, per unit charge. So potential energy per unit charge due to what? Due to the presence of other charges in a given region of space. So we can write something like U, or U sub E, is equal to Q times V. And then one last thing to recall, and this is mostly a Physics 1 concept, although we could have maybe used it, and certainly you'd see it in your textbook if you're taking Physics 2 and reading your textbook, is the relationship between force and work. And therefore between force and potential energy. So recall that work is given by W equals integral F dot ds, or dl. All right, so that's how you get work. It's the integral of force times displacement. And you can use this operational definition, potential energy is potential of some force to do work, so that you might write that U is equal to negative of the integral of F dot dl. Now, if you combine these statements together, it becomes apparent that the voltage V, remember that U is Q times V, so U must be equal to negative of the integral of F, that's Q times E, dot dl. And so I can easily divide out the Q's from all of these to get that V is equal to negative integral E dot dl. And typically what we do is we try to find the voltage drop between points A and B. So VAB is negative of the integral from A to B of E dot dl along the path taken from A to B. And I say the path taken, it actually could be any arbitrary path. The E will maybe change and the dl will maybe change, but this ends up being equal because we only care about start and end. So this relates V to E in an integral form. There's actually a reverse of that function. This is what a lot of textbooks actually present. So conversely, converse to this, we can say that E is equal to negative of the gradient operator of the potential. So these two statements more or less are, for our purposes, equivalent. So we could either do V is equal to negative integral E dot dl or ds, or we could say that E is negative gradient of V. And you may want to know, what is the gradient operator? So this operator del, it's actually called an operator, but we don't really have the vocabulary for that. Gradient of V is the derivative, actually partial derivative of V with respect to x in the I hat or x direction, plus the partial derivative of V with respect to y in the j hat or y direction, plus the partial derivative of V with respect to z in the k hat direction. So this symbol right here means partial derivative. Essentially, we treat x, y, and z as being completely independent of each other variables in whatever problem we're solving. Usually in space that's true anyway, but there are certain systems in which maybe it's not so true. The details of that kind of go beyond our class. So yeah, this is how we relate these two things to each other. This right here is what's called the gradient, or sometimes the gradient operator. So this whole thing would be gradient of V. This would be the gradient operator. You could think of the gradient as change or rate change in the sense of rate being per unit space, so spatial rate, if you will, of the potential, or whatever it is that you're finding a gradient of. So a gradient just is the spatial rate change of V per unit distance in some direction. You could say in the direction taken. And generally speaking, if it's not specified, if we just vaguely say what is the gradient of V, we usually actually can use it to mean in the direction in which V changes most rapidly. But as far as an operation is concerned, this right here is your sort of equation. And you can convert it into cylindrical or spherical coordinates, but again, that kind of is getting outside of the scope of our class to some extent. So let's maybe consider a basic example. One simple example for all this would be just kind of relating the E and V for a point charge. Okay, so for a point charge, you know that E should look like K times Q over R squared times R hat. Alright, so what that means is that V should look like negative of integral K Q over R squared R hat dot. Now we need a DL. Well, our DL vector, our most obvious DL vector, our rapidest change DL vector, if you will, would be dr R hat. And so if you do that integral, we've got an R hat dotted with an R hat. So R hat dot R hat is equal to 1. So that part of the integral goes away. And what I'm left with is just negative of, and I can pull constants out. So I have a KQ, so K Coulomb's constant times Q, integral of dr over R squared. So the integral of dr over R squared is just 1 over R. So my V should look like negative of KCQ times, I said 1 over R, it's actually negative 1 over R. This is R to the minus 2. So 1 over R squared is R to the minus 2. So add 1, and that's R to the minus 1, and now multiply by this, that's a minus 1. Okay, and so combine the minus signs, and I get V is equal to KQ over R, just as expected for a point charge. So that's consistent with the point charge. Now that's kind of in some ways like the trivial example. What if we kind of go in reverse, right? So what if we pick some other distribution? Maybe we pick a sphere. So maybe a more interesting question is, what would the electric field be due to, let's say, a sphere of charge, maybe like at the center of a partially hollowed sphere, kind of like the example I did in the previous video about our potential due to a point charge. And so you'll recall that the potential due to a point charge at some position was given by this long sort of equation. But we might ask, all right, well, what is the electric field at this position going to be? So I have like this uniform point charge. I ended up having this as my potential. So what is the electric field at this location, given this uniform charge distribution of Q and given this partial hollowing with these parameters? So recall that this is our voltage. Now to get E, we just need to take negative of the gradient of V. Now we could do that in Cartesian, but we could also do it in spherical coordinates. As it turns out, the spherical coordinates, this partial differential equation is a little weird. The first term, or leading term, is a d by dr. The others have some phi's and thetas and r's mixed in. It doesn't actually matter though, because if you look at this equation, you'll notice that every single term in the equation is constant. So in some sense, this ends up looking like dv by dr, or negative dv dr times r hat. But since all these are constants, it follows that E is equal to 0. Now this result may be a little disappointing. After all, we just got E equals 0, but it's one that we can actually verify. Remember that we've actually done this problem before, but using electric field lines, and we established that there was no way, if there's no charge in the center, for a field line to validly originate somewhere on the sphere and pass through the center area and then validly terminate somewhere else, not without crossing some other field line. In other words, we know that the E field actually radiates outward from this configuration. So this is actually kind of the expected result. All right, so if you're feeling cheated by those last two examples, I have actually a third example for you. This one, we're not going to give you a distribution of charge. Instead, we're just going to give you what the potential is in some region of space and ask what the E field is in that region of space. Okay, so the answer to that, or the way to solve that, is that E should look like the negative gradient of V. Okay, so that's going to be dV by dx I hat plus dV by dy j hat plus dV by dz k hat. All right, so in some sense what you're doing is you are looking at this equation and you're taking a derivative of only the x terms. So this right here is derivative of only the x terms. And that gives you that gives you a 3ax squared. This term right here is taking only the derivative of the y terms. So we're looking at this term right here. And so that is just going to give me minus b. And then the last term here is taking a derivative only with respect to z terms. There are none. So no z dependence. And what that means is that this term actually equals 0. So now put those three things together, and what you end up getting is that the E field in this region of space is negative of 3ax squared I hat minus b j hat. And you don't really need to put the k hat because it's 0 k hat. If you'd rather distribute the negative, you could just say minus 3ax squared I hat plus b j hat. And there you have it. Very straightforward, I hope. So notice that in this first derivative, this first term dv dx, we ignore the y and z terms and look only at the x terms. For this one, we ignore the x and z terms, look only at the y terms, etc. One last little caveat to this. If I have a term, and I'll just kind of put this as a sort of margin note. If I have, let's say, d by dx of a term that's like x squared y squared, or let's say y cubed. This one, it's not that we ignore the whole term, it's that we look only at the x parts of it, and so you end up with 2x y cubed. There's no further derivative to be taken here. If I want to take d by dy of x squared y cubed, what I would end up getting is 3, and the x squared part stays the same, and the y cubed term becomes a y squared term. If I want to take d by dz of that same term, x squared y cubed, there's no z terms to take a derivative of, so I get a 0. So hopefully that also helps clarify how the partial derivatives work. So yeah, this video went slightly longer than I'd originally anticipated because I gave you 3 examples rather than the usual one. Even if each one was a little bit shorter, they should give you enough to go off of. And hopefully you also have a little bit of understanding, enough operational understanding, let's say, of partial derivatives to be able to do them if you run across them in class, in your homework, etc. So hopefully you learned a bit from this video, and as always, thanks for watching.